Hey guys, welcome to A2. So this is our first topic in A2, and we're talking derivatives. So we're going to start with this concept that these guys developed a few hundred years ago. Newton and Leibniz, they figured out the concept of a derivative and figured out the derivative can be used to calculate the slope of the tangent to any point in a function's domain. So, you know that limit formula we learned a while ago with the h goes to 0, and we're trying to find the slope between 2 points, and we want those points to be really, really close together? Yeah, we're basically using that formula. So check it out. This guy right here, this formula, is called the first principles definition of the derivative. Definition of the derivative. So we call it first principles. And the formula looks like this. So let's say we have a function f of x. If we want to find the derivative of that function, we call that f prime x. Also, there's a bunch of other notations. A really popular one is dy by dx, which is just the change of y with respect to x, or some people just use y prime. So all of these notations are acceptable. I would say this guy, I remember seeing him mostly in university, but any of them work. Okay, so I'm just going to say f prime of x is equal to the limit as, h approaches 0 of f of x plus h minus f of x divided by h. So that should look so familiar to you because we basically did that when we were doing slopes of tangents, instantaneous rates of change, because that indeed is what a derivative is. It helps us find the slope at any point on our function. That's all it does. So at any point along the curve of a, say, parabola, we can find the slope of the tangent line at any point along the curve of a parabola using the first principles definition of the derivative. So in A2, we're going to focus on this first because it's your like roots. Like you need to know this. This is where derivatives come from. And then all these rules come out of this formula. We're able to make lots of conclusions and see patterns develop, and then it leads us into like power rule, product rule, quotient, all these really important rules that all come from first principles. Okay, so let's just get into it and try this formula. Okay, so let's say we're going to find the derivative of f of x is equal to x squared. So this here is our function. It's a quadratic. Why not? It's so familiar. So we're going to start with our quadratic, and we're going to find the derivative. And then we'll talk about what that means. Okay, so let's find the derivative of this function. So as you can see in our formula, we need to know f of x plus h and f of x, and it's going to be as h goes to 0. So first, let's just find out what all that stuff is. So we already know f of x is x squared. Okay, check that off the list. But what is f of x plus h? Well, it turns out anywhere in your original function, you're just going to put a plus h anywhere you see an x. So I see we had x squared. Now we're going to have x plus h squared. So just anywhere I see an x, I stick an x plus h instead. And I'm just going to expand that. So x plus h squared would be x squared plus 2xh plus h squared, right? Because x plus h squared means x plus h times x plus h. Okay, so now we know that. Check, check. So now if we want to find the derivative, f prime of x, we just use that limits formula. So the limit as h goes to 0 of f of x plus h, which I know is x squared plus 2xh plus h squared, minus f of x, which is just x squared, and then the whole thing is divided by h. Okay, so limit as h goes to 0. So I noticed that these x squareds cancel out. They're gone. And I've got 2xh plus h squared over h. Now I'm noticing a whole bunch of h's. So I think I'm going to factor them out, and then I can simplify this expression. So I'm going to factor out an h, so I have 2x plus h divided by h. And now that I've factored them all out, I can cancel out these h's. And I'm left with the limit as h goes to 0 of 2x plus h. Now I'm going to go ahead and sub in 0 for h, which means I don't write that limit thing anymore. Now I just actually sub in 0 for h. And I am left with 2x, which means the derivative of x squared is 2x. And what the derivative is, it just helps us find the slope at any point on our parabola. So for example, I'll just give you a visual here. Okay. All right, I'm going to sketch out my parabola. So I know it's 0, 0, 1, 1, 2, 4, 5, 6, 7, 8, 9, 3, 9. So I know this is what my parabola looks like. Just like this. So that's my original, f of x equals x squared. Now if I want to sketch on my derivative, 2x, I know it's got a y-intercept of 0 and a slope of 2. It's just going to be a straight line. Maybe I'll just use the straight line tool. See how that works out. Not bad. Ooh. Okay. So this is my derivative, f prime of x equals 2x. So just to try to explain this, so it just tells you that if you wanted to find the slope at any point on the graph of x squared, you could. So let's say we want to find what is the slope right at x equals 1. Well, it turns out you can just sub that into your derivative. So if you wanted to find the derivative when x equals 1, which also means the slope of your function at 1, it would equal 2. And we can see that on the graph. Right when x equals 1, our derivative is at the y value 2. And that, in fact, if you were to draw a tangent line at that point, the slope of that tangent line would be 2. If we wanted to find the slope at x equals 0, we would just sub 0 in to our derivative. So f prime of 0, 2 times 0 would be 0, which makes sense because right at the bottom of the parabola, we would expect it to have a slope of 0. And you can see that on the graph at x equals 0, it's got a y value of 0, which totally makes sense because at the bottom of a parabola, it's changing direction. It's heading, it's going down and then back up. So right at the vertex would be a slope of 0. If we wanted to find the slope at x equals 4, and we subbed it in, actually, I don't want to find that because I don't have it on my graph. If we wanted to find the slope at x equals 2, I would just sub a 2 into my derivative. So 2 times 2 equals 4, and that's right where they overlap on the graph. So at x equals 2, my derivative is 4, and so is the y value at that point. Okay, so that's what derivatives are. They just help you find the slope at any point on your original function. So we started with our original graph of x squared, our original function, and we found the derivative of that original function is 2x. So quadratic, the derivative of it became a linear function. Okay, let's try another one. So let's say you had, let's try a slightly harder one. So let's say you had f of x equals, say, 2x cubed plus, let's say, 5x. I wanted to do one that had multiple x's just so you could see what it's like. Okay, so now we've got a cubic function. And if we wanted to find the derivative of it, we're going to need our limits formula. So if we want to find the derivative, f prime of x, we're going to take the limit as h goes to 0. of f of x plus h minus f of x, and the whole thing's divided by h. So I always like to start, personally, you don't have to do this. I always like to start with my original. So I know that is what, like this is what f of x equals. So I got that. But I need to find out what is f of x plus h equal to. So anywhere I see, I just want to back that up a little, I'm not going to have room. F of x plus h. So anywhere I see an x, I just replace it with an x plus h. So I got 2 x plus h cubed plus 5 x plus h. Now I'm just going to expand this because definitely would be easier if I expanded it ahead of time. And this looks awful to expand. Like we have to expand x plus h times x plus h times x plus h. So I'm sorry, it does need more room. So if we expand x plus h cubed, we will get x cubed plus 2x squared h plus xh squared plus x squared h plus 2xh squared plus h cubed. Got, and that's just expanding this. Now we still have plus 5x plus 5h. Then I still have to go multiply everything in there by 2. Ugh. Okay, before I multiply it by 2, is there any like terms? I got an x squared h. Yeah, this and this. I'm just going to simplify what I have in the brackets first. So I got x cubed, and then I actually have 3x squared h. And then I have 3 of those. 3xh squared plus h cubed. Okay, a little bit shorter. Plus 5x plus 5h. Okay. And then I guess I'll just multiply it all by 2. So, sorry, I was just thinking. So 2x cubed plus 6x squared h plus 6xh squared plus 2h cubed plus 5x plus 5h. Okay, perfect. Now I'm going to sub it into my limits formula. I'm going to put my equals sign over here because I need so much space. You know what? I'm just going to move it down because I just feel like it's going to get in the way. Okay, so derivative is equal to the limit as h approaches 0 of f of x plus h, which is this whole thing. So 2x cubed plus 6h squared, or x squared h plus 6xh squared plus 2h cubed plus 5x plus 5h minus f of x, which is 2x cubed. And I'm going to put that as a minus 5x because, like, you know what I'm saying? If I had a minus sign in front of that, it's going to turn the 5x minus or negative 2. Everything's divided by h. Okay, whew, this is a tricky one. The algebra is crazy. Okay, so I'm noticing 2x cubed minus 2x cubed is gone. 5x minus 5x is gone. So that's nice. Cancel some stuff out right away. And I'm also noticing every term that I have left has an h in it, as usual. So I'm going to go ahead and factor out an h. So this will become 6x squared. Took care of that guy. And then I got plus 6xh. Took care of that guy. Plus 2h squared. That's that guy. Plus 5. I think I got everything. Divided by h. So now my h's can cancel. And I'm left with the limit as h approaches 0 of 6x squared plus 6xh minus 2h squared plus 5. So now I can go ahead and sub 0 in for h. So that's going to leave me with 6x squared. That's going to be gone. That's going to be gone because once I sub a 0 in, 0 times 6x will be 0. And 0 squared times 2 will be 0. So then I just have the plus 5. which means the derivative. So our original function was, our original f of x was, let's just see, 2x cubed plus 5x. 2x cubed plus 5x. That guy was our original function. And this is the derivative. So the derivative of a cubic function is a quadratic. So that's neat. So now we can find the slope at any point on this curve. So at any point on a cubic function, you could find the slope. Let's say I want to find the slope. So let's say it said like, find slope when x equals -3. Totally, we could do that. So we just take the derivative and we sub in -3. So 6 times -3 squared plus 5 is equal to 6 times 9 plus 5. And 6 times 9 is 54, plus 5 is 59. Trying to think what else. I guess that's it. So I guess the main concepts of this are that we want to be able to find the slope of the tangent to any curve, and we do that by using first principles to get the derivative. I'm trying to think of anything else I want to tell you guys. Sorry, I should have figured that out. I guess just one more thing about notation. So I keep using f prime of x, but Leibniz notation is more popular, especially in universities, and that's the dy by dx. So it can simply replace the f prime of x. Like, they mean the same thing, they just mean the derivative. Also, this dy by dx can also be written as, like with the f of x, you can put it like this. Because f of x is just replacing y. So it's just saying to, it's just expressing the derivative of the function, f of x or y. So all of these things are just notation for the derivative. But I did find in university they seem to stick to this form, and it does help you when doing, well, we'll talk about it later. And just to note that this doesn't denote a fraction, it's just a notation. So maybe this is like slightly simpler notation, but in many cases the Leibniz notation is preferable. It communicates the relationship, like the change in one variable with respect to another variable. So that's kind of helpful, especially when you do like certain problems like with heights and stuff. Like, you can identify which one's the independent variable and the dependent. Like if you're doing like volume with respect to temperature, you could denote it using the Leibniz notation. All right, guys, more on this later.